In this video, we're going to discuss the mean value theorem. This will look very familiar because it is actually just a generalization of Rolle's theorem. So let's suppose that y is equal to f of x is continuous on a closed interval a to b and differentiable on the open interval a to b. Then there's at least one point c in a comma b at which the derivative is equal to the slope of the secant line between those points. So let's look at a picture to really try to see what's going on. So suppose we have some continuous function on this closed interval. Then if we have the slope of the secant line between a comma f of a and b comma f of b, then we look at this slope. There is some point, at least one, in between a and b where the tangent line on this function has the same slope of this secant line. And in fact, that occurs at 2 points on this particular picture. And they are approximately at these locations that I've just drawn now. Again, what does the mean value theorem say? The mean value theorem says that there only guarantees at least one here, right? So in this particular picture, we ended up with 2. And we may have many more than 2. In fact, that number could be arbitrarily large. But we'll always be guaranteed at least 1. And again, this is just the generalization of Rolle's theorem. Because what did Rolle's theorem say? Well, Rolle's theorem said that f of b was equal to f of a. In other words, this slope of the secant line was 0. And then Rolle's theorem said that the derivative would be 0. There would be a point somewhere in between where the derivative was 0. Okay. So, let's look at an example where we use this. Let's verify the hypotheses of the mean value theorem, abbreviated MVT here, on the interval -2 to +2 for f of x equal to x cubed minus 3x plus 2. Oh, sorry. And let's see. Then find all C which satisfy the conclusion of the mean value theorem. First off, what are the hypotheses of the mean value theorem? Well, that is just the 2 statements that the function is continuous on the closed interval and differentiable on the open interval a to b. We have a polynomial. F of x is a polynomial. And thus differentiable and continuous everywhere. Okay. If that is differentiable and continuous everywhere, then our hypotheses for the mean value theorem are satisfied. Now, what is the conclusion? The conclusion is that there is at least one point C between -2 and +2 in which f prime of C is equal to f of B, so f of 2 minus f of a, so f of -2, all over b minus a. All right, so we plug in 2 here. 2 cubed is 8, minus 6 is 2, plus 2 is 4. Minus, plug in -2 here, it's -8, plus 6 is -2, plus 2 is 0, all over 4 here, and we get 1. So there is some point C where the derivative is 1. Well, let's find that. How do we do that? Well, what is f prime of x? That is 3x squared minus 3. And we want to set that equal to 1. This implies that 3x squared is equal to 4. So x squared is equal to 4/3, and x is equal to plus or minus the square root of 4/3. And in fact, what this tells us is that we found 2. There was at least 1, but it turns out that there were 2. Both of these values are between -2 and +2, so both satisfy the conclusion to the mean value theorem. Now, 2 last things to write down about the mean value theorem. Well, one thing I should say is the proof of this is not too difficult, and the main use of Rolle's theorem is actually to prove the mean value theorem. So the proof does require Rolle's theorem, and using Rolle's theorem, the proof of the mean value theorem is not too difficult. But I will leave that out of this video for the sake of expediency. Now, what can we do? I'm going to, again, leave out the proofs, but the mean value theorem can be used to prove the following 2 statements. The first statement is that if f prime of x is equal to 0 at each point x of an open interval a to b, then f of x is equal to c, some constant c, for all x in the open interval a to b. And again, I said this in words, but I'll write it down, for some constant c. Okay. Right, so what does this say again? This just says if the derivative is 0 everywhere, you have a constant function. The proof of that, though, requires the mean value theorem. Easy enough statement that you probably already believe, but the proof requires something a little bit more complicated, like the mean value theorem. All right, so the second statement that the mean value theorem can prove is a corollary to this previous one, and that is that if f prime of x is equal to g prime of x at each point x in an open interval a to b, then there exists some constant c such that f of x is equal to g of x plus c. In other words, f minus g is a constant function on the open interval a to b. And for clarification, when I say some constant c such that f of x is equal to g of x plus c, it's true on the entire open interval here, for all x in that open interval. All right, and that is where we will conclude this video.